right, so we're going to start today. First topic is Coulomb's law, which is the law governing electric force. Okay, so the question that Coulomb's law is going to help us answer. Okay, so let's say I take two protons and I position them 2 meters away from one another. A natural question is, how hard of a push does each proton feel from the other one? So you guys should all have learned from chemistry or bio or from general life experience that if you have 2 positive charges or 2 negative charges near each other, they don't like that very much, and they experience a repulsive force. They don't get sucked towards each other. If they're the same sign, they will repel each other. So these 2 protons are each going to feel a push away from one another. And the question is the force 2 newtons, 10 newtons, 1,000 newtons? How can you calculate that? And Coulomb's law is the formula that tells you how big the push is. Okay, so first, though, we're going to answer just what direction is the push on each proton. And you do this without Coulomb's law. You just look at the problem. You look, you say, oh, there are 2 positive charges, so they're each going to experience a push away from the other one. The one on the left experiences a push to the left, and the one on the right experiences a push to the right. And we're going to be taking this approach in pretty much every electrostatics problem. We're going to draw the direction of the force first, and then separately compute the size of the arrow, how big, how many newtons it is. And the equation for getting the size of this arrow, and this is called Coulomb's law, is that the size of the force is this constant called k. It has a value that I'll write down later, 9 times 10 to the 9th, times the charge of the first object involved, times the charge of the second object involved, all divided by the distance between them squared. Okay, so I'm just going to write some little arrows here. This is going to be something I'll do all semester. R is the distance between the objects. Q1 and Q2 obviously are the charges of those 2 objects. But the charges are going to be in coulombs. And K is just a numerical constant, it's just a number. And again, it's 9 times 10 to the 9th. And the units on this are pretty foul. It's newtons times meters squared per coulomb of charge squared. Okay, a coulomb, just a side note, so a coulomb is a new unit that you're meeting right now. A coulomb is a unit of charge. It describes how much electrical stuff is on the object. And a number you're going to want to remember that I will write down later is that the charge on a proton is defined as this letter E, and it is 1.6 times 10 to the negative 19th coulombs. Okay, so it's a very, very small amount of charge on each individual proton. The electron, it has minus that number. It is minus 1.6 times 10 to the negative 19th coulombs. So same size of charge, same magnitude, but opposite sign. So with this equation, we can now answer a question of how big is the push. Let me see. Yeah. Okay, so if we plug in our numbers, we have that the force is K, which is 9 times 10 to the 9th, times the charge of the first object involved. Remember, this always occurs as like a pairwise interaction where one object is pushing another. So the first object involved is the proton feeling the force. Second object involved is the other proton. And we divide it by the distance between them squared. Okay, and you guys are going to learn to become friends with your graphing calculator, specifically the EE key, the raised to the power of 10 key. If you punch this out, you're going to get a force of 5.8. Times 10 to the negative 29th newtons. Okay? And now, at this point, people often get confused about something. They often wonder, all right, so is that the force that is like in total felt by the two objects? Like there's two pushes going on. Is each one feeling 2.9 times 10 to the negative 29th? And the answer is no. Each arrow is this big. Okay, so this guy on the left experiences a push of 5.8 times 10 to the negative 29th newtons. And at the same time, the guy on the right, you use the same formula to compute the force on him. It's just Q1 and Q2 swap places. It doesn't matter which is which. He also experiences a force of the same size, but since we made our sketch at the beginning, we know it goes in the opposite direction. Right? It's a push to the right of size 5.8 times 10 to the minus 29. A common question then would be, what's the acceleration of one of those charges? So to get the acceleration from our old friend F equals ma, you can just divide the force, which is 5.8 times 10 to the minus 29, and divide it by the mass of a proton, which I have written down. There's, by the way, at the end of the slide, there's like a reference table of all the common masses and charges you'll need. But a proton's mass is 1.67 times 10 to the minus 27th kilograms. And that comes out to, if you do the division, 0.03 meters per second squared. And again, each proton is feeling a push that big, so each proton accelerates this way, but in different directions. Now, let's change the question up. Oops. Okay, the mic is pretty sensitive. Let's change the question up just a little bit. Oops. Let's say one of the protons was an electron instead. Okay, in this case, you have two charges of opposite sign, and as always, we're going to try and draw the direction of the force, and then later we will worry about exactly how big the force arrow is. So opposite charges are going to attract each other. So the proton is going to feel a pull to the right towards the electron. The electron is going to feel a pull towards the left towards the proton. Okay, we've drawn the directions of the arrows. Now let's just write down how big those arrows are, and then the problem will be done. So to compute the size of this arrow, we're going to do just, again, k times the charge on one of the two objects. So we'll do the charge on the first one. Times the charge of the second object. So this is an electron, so technically its charge is negative 1.6 times 10 to the negative 19. But I want to point something out. The negative sign always communicates the direction of the force arrow. So if you have two positive charges, the force is just in the direction that you drew the arrow. When you're working with a negative charge, and this will require some getting used to, by the way, when you're trying to write the size of the arrow, you've already pinned down its direction. You don't want to flip its direction around with minus signs again. You already got the fact that there's a negative charge involved. So you're actually just going to use the size of the charge on the two objects. So really, I should note, if you're going to take this approach, which we always will, of drawing the directions of the arrows first, and then finding the size of the arrow, you always are going to use k times the magnitude of q1 times the magnitude of q2 over r squared. And again, this is the length of the arrow, and you've determined the direction that the arrow is pointing in a separate way. If you were to accidentally use a negative sign here again, you would find that the pull is negative to the right for the proton, which is not what it actually is. Okay, we're going to do one quick more slide, and then we'll move on to our first example. Okay, well, this actually will serve as a motivating example. When there are multiple charges involved, all you're going to do is, on whatever charge you're being asked about, as usual, stick to your guns. You draw the directions of the push from each of the other charges involved. In this case, I'm asking about the push that the 3 Coulomb charge on top in black experiences. So what I want you to do is draw the directions of either the pushes or pulls from the other 2 objects. Later, using Coulomb's law, we're going to find the size of those 2 arrows. And then remember, they're 2 forces. They add up together as arrows. So if you have one force pointing up and another force pointing down, to get the net force, you should be subtracting the 2 from each other, because the push upwards is fighting against the pull downwards. Any questions before we start this example? You can also ask me as I wander around the room. All right, so work with either the people near you, and at the end, I'll give you about 3 to 4 minutes. Hold up the ABCD cards. Guys, here, they're not protons. They're charges of size 3 coulombs, -5 coulombs, and 10 coulombs. These are big-ass charges. All right, who still needs more time? Please raise your hand if you need more time. All right, I'll give you guys about like 30 more seconds. Don't worry if you don't finish it, it's okay. All right, on the count of 3, hold up your ABCD cards. You can put up like the blank side if you like didn't get the answer. All right, 3, 2, 1, go. Okay, I see a splattering between A, B, and C. The answer is A. And I want to go through this. Quiet down, quiet down. All right. I want to go through this because the minus sign thing is one of the few things that I can't really teach too directly. It kind of needs to be felt out, and the minus sign error would cause you to pick choice B. So I'm going to do the problem now, and we're going to see how this goes. Okay, so we're finding the forces on the 3 Coulomb charge up top. Okay, so first, as always, I'm just going to draw the direction of the pulls or pushes coming from the other 2 charges. So due to the negative charge, it's going to experience a pull downwards because it's attracted to the negative charge. And by the way, I'm going to do this I'm going to write on the figure in a way that I consider to be very efficient. So if you want to try and mimic what I do in your own problems, it might save you time and clean up your work a little bit. All right, 3 Coulomb charge experiences a pull due to the -5 Coulomb, but it also experiences a push upwards because it's repelled by the 10 Coulomb charge. So there's an upwards force due to the 10 Coulomb charge. All right, now we have the forces drawn. Let's just write down the sizes of each pull or push. Okay, the size of this pull right here, remember to do the size of a pull, you do K times the size of the first charge times the size of the second charge divided by their separation squared. So we're going to do K times 3 coulombs times 5 coulombs. Again, I'm using the positive number, and the fact that it's a negative charge is communicated in the fact that the arrow is going down towards the other object. Okay, and then I divide it by their separation squared, which is 3 squared. Okay, now if you punch this into your calculator, you get 1.5 E10. Again, E refers to 10 times 10 to the 10th. Okay, same thing due to the blue charge. Let's figure out how big of a push that is going vertically upwards. Okay, to get the size of the push, I'm going to do K, which is again just 9 times 10 to the 9th. I'm going to multiply this size of the first charge, 3, times the size of the second charge, which is 10 coulombs. And then here's where some people might have gone wrong. You divide by the distance between this charge and this charge squared, which is 4 meters squared. This is something that I do not because I hate you, but because it'll pop up on the homework, and I want you to catch it now. And if you punch this into Wolfram or your calculator of choice, you should get 1.7 times 10 to the 10th. Okay, so here's the situation. We have a pull of like 1.7 times 10 to the 10th upwards, and then a slightly smaller pull that is fighting it, 1.7. The answer is B, not A. I'm dumb. All right, that's good, because a majority were B, and I was like, everyone's making a minus sign mistake. All right. Hold on. What a great start to my first example in this class. Okay, so you have a 1.7 force pointing upwards and a 1.5 force pointing downwards. Now again, you don't just add their sizes because they add as arrows. It's an upwards pull compensated by, fought by, a marginally weaker downwards pull. It's like if you pull upwards 30, you pull downwards 10, you end up with upwards 20. So you're going to subtract 1.5 E10 from 1.7 E10, which gives you 0.2 E10 upwards overall, right? The upwards pushing force wins because it's slightly bigger, and it's in the direction upwards. And 0.2 times 10 to the 10th is 2 times 10 to the 9th. Does anybody have any questions about this? This is a very fundamental example. We're going to use it a lot. Yes? Sorry, say one more time. Oh, he asked, is the system in equilibrium? That's a good question. So whenever I draw these problems, you assume the charges are just nailed into the board. If you were to let these go, they would fly towards each other or fly away from each other. But unless otherwise told, you just assume the charges are glued to where they are. They're experiencing pushes, and hypothetically, if you let them go, they'd try and fly away. But you always assume that they're pinned in place. Any other questions on this, guys? Good job. All right. We're going to approach something that you're going to use a lot more, which is when there's, quiet down. Just for the people in the back, thank you, I appreciate it, guys. When there are multiple charges involved, and I make you do this, again, not because I hate you, the problem is going to be one of these, where there's triangles involved, but because this is something we're going to do with electric field for the next couple weeks, and then later with magnetic fields. This is basically a intense review of like vector addition and that to make sure everything's all square. And again, I'm going to show you a method after we do the example that I think is very clean and will help you avoid any unnecessary mistakes. You're free to adopt it if you want. So just a quick remark on how you approach these harder examples with multiple charges. As always, still, you're going to want to draw the directions of the forces first. Sorry, actually, I went with that. Okay, so just like in that last example, how I drew the directions of the arrows, whether they were up or down first, and then worried about the sizes later, that's always a good strategy to have to avoid faking yourself out into thinking it's more difficult than it needs to be. Afterwards, you'll find the size of each force. And again, you're going to do that using K, Q1, Q2 over R squared. You'll compute that number and then write it next to the arrow. Okay, and then part 3, and this is the part that is kind of annoying, is you have to add the arrows together. And notice how I said you add the arrows, not the sizes of the arrows. And since you're adding the arrows, just like in the last example, if they point in opposite directions, you will have to subtract. And in the example we're going to do, if the arrows aren't even on the same line pointing in the opposite directions, if they're pointing in random directions, you are going to have to add them like by adding their x components and y components. So you're going to have to do trigonometry. So again, you're going to have to if they're not on the same line, you'll have to add their x components together to get the x component of the new total arrow. And so on for the y component. You have to add the y components of the two arrows being added to get the y component of the new arrow. So rather than doing an in-depth trig review, for the next pretty much 20 minutes, we're going to just do an example on this. This one will appear on the homework. I think I assigned a similar problem 2 to 3 times. Again, they're a little annoying algebra-wise, but if you keep them relatively clean, you shouldn't have that much trouble with them. They are a little bit annoying, but it is important to be able to add these consistently. Okay, so I'm going to turn you loose on an example. We're going to work on it for about 15 minutes. I'll go over how it works, and then at the very end of class, I'm just going to say one more quick slide about a specific homework problem. Okay, so let me just explain the example for a second. All 3 of these are positive charges. And I'm asking you, what is the direction and size of the force on the 2 Coulomb charge? Okay, the direction and the size. So you're going to need to use some trigonometry for this to find when you actually add up the arrows. And the answer is up there as far as I know. Hopefully I'll get it right this time, even though I do these beforehand. All right, so I'll turn you loose. We'll do the ABCD cards after. Again, please do ask me questions as I walk around the room. That says find force on this guy. I'm going to slowly start writing a couple steps up there in case you get faked out and you're behind. I'll slowly write, but you should be ahead of me still. Did everyone get the size of these two arrows all right? Good, okay. Next thing is going to be you have to find the angle of the arrows. I'm going to redraw those arrows in the bottom corner with all my angles and lengths labeled here. How we looking, guys? So here I wrote the two arrows, And I broke the diagonal one into its x part and its y part by using trig. Question? No. All right, who still needs more time on this one? Okay, a fair bit are actually done. All right, just in the interest of time, we're going to take about 30 more seconds and I'll go over it. All right, show me your cards on 3. It's okay if you didn't finish. I just want to get to something so you guys can do a little bit more on the homework here. All right, 3, 2, 1, go. I like what I see. All right, the answer is B. Probably about 75% of you got it. Don't worry if you got C. I'm going to walk you through it, and maybe you'll see your mistake. But there's also just a fair chance the algebra got off somewhere. I just randomly created those other answers, so it's not like you made a systematic mistake. So I bet you just maybe punched in something. Maybe you were in radians. Maybe you forgot to carry the power of 10. So I'm just going to go over this real quick. All right, so as always, your first step is to draw the directions of the push on the charge of interest. So I drew this red arrow right here and the blue arrow right here on the charge, and I found how long each of those arrows was afterwards using Coulomb's law. Okay, I had to use 5 meters in the denominator here because that's how far away the 2 and the 3 are from each other. You can't just do it's 3 and 4. You have to use the hypotenuse there. Okay, once I have those 2 arrows, it's just a matter of annoying trig and bookkeeping. So I redrew my arrows down here. Come on. I redrew my arrows down here, and I know that this angle right here is the same as this one, so I found that using trig as well. I took the arctan of 3, the opposite, over 4, the adjacent. Now, the instruction, the last part of the problem is I need to add these 2 arrows together, but unlike in the last problem, they aren't on the same line, so I can't just add or subtract their sizes. I need to break up the diagonal one into its x and y components, which I again do using trig. So to get this side, I do the hypotenuse times cosine of 36.9, and to get the vertical side, I do it times the sine of 36.9. Now we're going to add these arrows together by adding their vertical parts. So the new vertical part is 8e9 plus 1.32e9. And then the new horizontal part is just, since the other one doesn't have a horizontal part, it's 1.76e9 to the right. Oops. What? Okay. 1 second. Sorry about that. Okay, so you have that push upwards and this push to the right. And the last step is to combine these into a new arrow. I'll quiet down a little bit, quiet down a little bit. So to find the length of this arrow, use the Pythagorean theorem to find the hypotenuse. So square root of this squared plus this squared gives you 9.5 E9. And to get this angle right here, you're going to take the arctangent of this number divided by this number. If anyone is confused about this, by the way, because I know I'm going a little bit fast to wrap up, please do bring it up to me and we can work through it. If you take this, you'll get 10 degrees. So that gives us B as the answer. All right, one more thing before we end. All right, one more thing here, one more thing. All right. So I want to call to your attention the fact that you're going to see Coulomb's law in a form that's different than the one that I showed you. So I showed you that you assign the direction manually and that you just work with the size. If you look in a textbook, you're going to see this equation. So this is what I had. You're going to see this in a textbook. Okay? What this means is that the force arrow points in the direction of the r hat arrow. R hat, this is a very unusual thing, but people use it a lot. R hat, it points away from the source charge and towards the charge that is feeling the force. I'm going to call that the experiencer. That way, if Q1 and Q2 are both positive, the force arrow points away from the source. And if Q1 and Q2 are opposite signs, the opposite, when you take the negative sign in front of the r hat arrow, it's going to point towards the source. So this sort of combines the attraction and repulsion into one equation. However, the way that we did it is the way that I think you should attack most problems. Just be aware that you will see this in your textbook. All right, great job, guys. Thank you for working together on those problems. I appreciate it, and I'll see you on Friday.